Hey everyone, it's Bradley Bush with another algebra video. Today we're talking about modeling exponential growth and decay. We'll talk about quick overview of decay and growth models. Then we'll talk about carbon-14 and the Dead Sea Scrolls. I think that this is probably one of the most classic examples of exponential decay. I think I've seen it in every algebra textbook I've ever looked at, and I think it's an applicable and real-world interesting example. So let's do that. So first off, the model overview. So models, exponential growth and decay models, generally model some type of population. So the population could be humans, it could be a virus, it could be bunnies, it could be a bacteria, it could be anything, but it's something that is growing or decaying. It could be a substance like radioactive decay, material that is decaying and they're monitoring the radioactive decay. It could be carbon-14 that decays according to a certain rate. So there are a lot of things in life that either grow or decay at a given rate, and these models are great ways to describe them. So we have to have an initial amount, right? If you're modeling a bunch of bacteria, you put a bunch of bacteria in a petri dish and say you've got 200 you put in there. Then the initial amount would be 200. The initial amount is represented by A0. That 0 to the bottom right of the A represents initial value, and it's said A0. So A0 is the initial amount. Then time starts ticking, and time is represented by T in our models. So time starts ticking forward, and at any time T, if we stopped the time, say at 5 days, then the amount of that substance that we would have at that time would be A on our model on the right, or F of T on the model of the left. And the difference between A and F of T is just whether or not you want to use function notation with the F of T, or you don't want to use function notation and you use A. So A kind of would be similar to using Y instead of F of T. So we also have the natural exponential. So this exponential model has a base E. That's awesome. And the last thing is we have the growth constant here. So the growth constant is either a growth or a decay constant, and it is a growth constant if k is positive, and it's a decay constant if k is negative. A0, A, and K are all real numbers. That's what that script R means. And the little E-looking thing is really an epsilon, and it means belongs to. So really all you're saying is A0, A, and K belong to the group of real numbers, meaning they're real numbers. T is your time variable, and it usually starts at 0 for when your experiment starts and then moves forward in the positive direction. And K, which is your growth constant, can't be 0. So let's move on. Let's talk about a graph. If you have a growth model, then you'll start with A0, and as time moves forward, you're moving to the right and your population gets bigger, so your graph goes up. If you have a decay model, you'll start with initial amount of substance, say radioactive material, and as time moves forward, you're moving to the right on the graph, and the amount of radioactive material decreases, so your graph goes down as you go from left to right. Pretty straightforward. All right, let's talk about carbon-14. Carbon-14 is a substance that is in any living organism, and it starts to decay once that organism dies. So the Dead Sea Scrolls were wrapped in a type of parchment, and the wrappings were made from some sort of plant material. So when those plants were harvested to create the wrappings, the amount of carbon-14 that existed at that time started to slowly decay. Well, good for us, carbon-14 has a half-life. That means the specific amount of carbon-14 that was present in those wrappings decays at a given rate, meaning every 5,715 years, half of what was originally there is gone. So they harvest the material to make the plant material to make the wrappings, and the time starts ticking. 5,715 years later, half of what was originally there is now there. Then time keeps ticking, and in another 5,715 years, half of what was there the last time is now there. So now we have a quarter of the original, because at first we cut half, and then we cut half of half, which gave us a quarter, and then we go half of a quarter, which is an eighth, and we just keep every 5,715, we slice what was there in the previous time step in half. So that's the concept of a half-life. So our problem says, assuming the wrappings of the Dead Sea Scrolls contained 76% of their carbon-14 when they were discovered in a cave by a young Bedouin shepherd, how old were they when they were found? So if we want to figure this out, then we need to know what K is, first of all, because we have to have some type of a decay constant. And we know it's going to be K because carbon-14 decays over time. So K is going to be negative, but we've got to find it out. So we've got a few constants here. We need to figure out a way to insert values for each of these variables except K and then solve for K. Well, we don't know how much carbon-14 was originally there when the plants were harvested to make the wrappings. So even though we don't know that, we're going to still put A0 there, and hang on, you'll be surprised at how this turns out. So we have e to the k times t, and this equals, well, whatever's there at time t, so some portion of A0, right? After some time t, what was originally there decays, and we have some fraction of that amount. Here's where we can use the half-life, because instead of having t, we can put there 5715, because we know in 5715 years, or 5,715 years, the amount that was originally there will be cut in half. So times 0, we have A0 amount, whatever it is, however much there was originally of the carbon-14 in the plant material. And after 5,715 years, we now have half of the original. So the cool thing about this, if we set it up this way, is that we don't even need to know how much was originally there, because it's just a constant that's on both sides of the equation, and we can just divide it out. So it cancels out and is gone. So what we have then is 1/2 equals e to the k times 5715. Now we can take this and we can say, hey, let's take the ln of both sides of the equation, because we want to get that k out of the exponent. And one great way that we do that is taking the natural log of both sides of the equation. So we do that. And when we do that, the e and the ln cancel out, and we are left with ln of 1/2 equals k times 5715. Now, what we want to do is divide away what we don't want, right? We don't want that 5715 there, because that's what we're trying to solve for. So If we divide both sides by 5715, then the 5715 cancels on the right-hand side, and we're left with k, which is what we want, right? That's exactly what we want. So k then is natural log of 1/2 all over 5715. Now, what is that going to be? Well, let's see. The natural log of 1/2 all divided by 5715. That tells us that k is approximately equal to, we're going to round, k is approximately equal to negative 0.00012. So now we need to update our model, right? So now our model is f of t equals a naught times e to the, instead of having k, we have our decay constant. So we have our model. They want us to tell them how old the Dead Sea Scrolls were when they were found in 1947. So we put in what we know and then solve for t. So we know the growth constant, we've already put that in, or the decay constant, I should say. We don't know how much was there of the carbon-14 when the plants were harvested, but that's okay because we know when they found the scrolls in 1947, they had 76% of what was originally there. So we plug in 0.76 times a naught. So we have our original amount, and then we have our original 76% of our original amount on the left. And the cool thing is, again, the a naughts cancel, and we're left with 0.76 equals e to the negative 0.00012 times t. So the a naughts cancel. And we're solving for t now. Now we want to solve for t. So we need to get t again out of the exponent. So if we take the natural log of both sides of the equation, just like we did in our last step, we'll take the ln of this, of 0.76, and we'll take the ln of e to the negative decay constant times t. What happens on the right-hand side, the ln and the e cancel, and we're left with the ln of 0.76 equals negative 0.00012 times t. And now we're going to divide away what we don't want, right? So we divide both sides of the equation by negative 0.00012. The decay constant cancels on the right hand of the equation, and we have t equals the natural log of 0.76 over negative 0.00012. And what does that give us? What does t equal? We'll probably be approximating here, but let's find out what t equals. So if we clear that, let's say the natural log of 0.76 parenthesis divided by negative 0.00012. 2286.9. So 2,286.9 years. So if we round that to the nearest year, then that gives us 2287 years old. So the Dead Sea Scrolls were about 2,287 years old when they were found in 1947. If you were asked to find out how old they were currently, then you would just add however many years have passed since 1947 to the present day to the 2,287 years. And there you go. There's a classic example of exponential decay with reference to the Dead Sea Scrolls and carbon-14. Thanks for watching. If you have questions, let me know.